Hello and welcome, and in this video I will be demonstrating how to take the derivative of these functions: e to the power of x, the natural log of x, sine of x, and arcsine of x. And before we get into it, I've written up some useful definitions. This is the full definition of a derivative. So the derivative of f of x is equal to the limit as h is approaching 0 of f of x plus h minus f of x all over h. And e could be defined as a limit where n is approaching 0 of 1 plus n to the power of 1 over n. And we'll actually need this definition of e to prove the derivative of this first function, e to the power of x. So let's just get right into it. So the derivative of e to the power of x by the definition of the derivative just be equal to the limit as h is approaching 0 of e to the power of x plus h. Because if f of x is e to the power of x, then f of x plus h must be e to the power of x plus h. Minus our f of x, which was just e to the power of x, and this goes all over h. Now, due to the exponent laws, we can rewrite this e to the power of x plus h as e to the power of x times e to the power of h. So this is really just equal to the limit as h looks like an n. Maybe I should make this thing taller so you can see that it's an h. As h is approaching 0 of e to the power of x multiplied by e to the power of h minus e to the power of x all over h. Now notice that both this term and this term contains e to the power of x, so we can just factor it out. So this will be equal to the limit as h is approaching 0 of e to the power of x multiplied by e to the power of h minus 1 all over h. But notice this limit is only affecting h. It is not affecting x in any way. So we may as well just move this e to the power of x to the outside of the limit. So this is really equal to the limit as h, or sorry, I meant this is equal to e to the power of x multiplied by the limit as h is approaching 0 of e to the power of h minus 1 all over h. And the easiest way to proceed from here, in my opinion, is via substitution. So I'll define n to be equal to e to the power of h minus 1. Then n plus 1 will be equal to e to the power of h. Then ln of n plus 1 will be equal to ln of e to the power of h. But that is just h, because e raised to the power of what is equal to e to the power of h. That what, of course, has to be h. But notice, if h is approaching 0 and n is defined to be e to the power of h minus 1, then n must also be approaching 0. So this entire thing may be rewritten as e to the power of x multiplied by the limit as n is approaching 0 of n, because that's just what we defined the numerator here to be equal to, divided by, and h was just ln of n plus 1. Now we can multiply both the numerator and the denominator by 1 over n. And this entire thing will be equal to e to the power of x multiplied by the limit as n is approaching 0 of, and n multiplied by 1 over n is of course just equal to 1 divided by, and when we have something multiplied by a logarithm, we are allowed to move this something up into the exponent of what is inside of the logarithm. So this thing is really equal to ln of n plus 1 raised to the power of 1 over n. But notice, the limit is only affecting n, and we only have n's inside of this logarithm, so we might as well just move this limit inside of the logarithm. So this thing is just equal to e to the power of x multiplied by 1 over ln of the limit as n is approaching 0 of n plus 1 raised to the power of 1 over n. But pay attention here. What is this thing inside of the logarithm? Well, notice that this is just a definition for e. So we may as well just write e inside of this ln. So this is really just equal to e to the power of x multiplied by 1 over ln of e. What is ln of e? E raised to the power of what is equal to e. Then that what, of course, has to be 1. So this is just equal to e to the power of x multiplied by 1 over 1 is of course just equal to 1. And this is of course equal to e to the power of x. And yeah, we're done here. Now we have proven that the derivative of e to the power of x is equal to itself. And now on to the next function, which was just ln of x. And I think the easiest way to do this is by utilizing the chain rule, logarithm laws, and implicit differentiation. So the logarithm laws tells us that e to the power of ln of x is equal to x. And now let's take the derivative of both sides. So let's cover all of this with a d over dx. And we've just proven that the derivative of e to the power of x is equal to e to the power of x. So on the left-hand side, we know that by the chain rule that e to the power that the derivative of e to the power of some function will be equal to e to the power of this function multiplied by the derivative of this function d dx of ln of x, which is really what we're looking for, will be equal to the derivative of x, which is just equal to 1. And let's divide both sides by e raised to the power of ln x, and we see that the derivative of ln of x is equal to 1 divided by e raised to the power of ln x. But what is e to the power of ln x? Well, as we already said, this was just equal to x. So this entire thing is really just equal to 1 over x. Yeah, now we're done. We've proven it. The derivative of ln of x is equal to 1 over x. Oh wait, maybe you can't see everything. Yeah, you should see it now. The derivative of ln of x will be equal to 1 over x. And we are done. And on to the next function, which was the derivative of sine of x. And I think this will be the most difficult thing to prove in this entire video. So the derivative of sine of x, by the full definition of the derivative, would just be equal to the limit as h is approaching 0 of sine of x plus h minus sine of x all over h. And now we can utilize the formula for sine of two added angles. So this will be equal to the limit as h is approaching 0 of sine of x times cosine of h plus cosine of x times sine of h, and now we still have to subtract our sine of x, and this all goes over h. But notice that both this term and this term contains a sine of x, so we might as well just factor it out and rewrite this as the limit of h approaching 0 of sine of x multiplied by cosine of h minus 1 plus, and now we still have to add this, cosine of x times sine of h, and this all goes over h. And now I think the easiest way to proceed from here is to split this up into two different limits, as this will just be equal to uh, this will be equal to sine of x multiplied by the limit as h is approaching 0 of cosine of h minus 1 over h plus, let's put a parenthesis over here, and we're fine with moving out this sine of x outside of the limit, because the limit is only affecting h, it is not affecting x. And now we can do the same thing to this cosine of x plus cosine of x multiplied by the limit as h is approaching 0 of sine of h over h. Notice that in both of these limits we have a 0 over 0 over 0 scenario, so we can't just plug in 0 into here and be done, because cosine of 0 is 1 minus 1 is 0, and divide by 0, it doesn't work. And same thing here, sine of 0 over 0 is another 0 over 0, which is undefined. So in order to proceed, we need to prove what these two limits are equal to, or we can't continue with the proof. Uh, but in order to prove this limit, we actually need to prove this limit first. So let's start with that one. And in order to do so, I will draw some shapes within the unit circle. Say we have a unit circle here. It's and we have some angle here. Let's call it theta. Let's say it goes like this. And now I want you to think about different shapes contained in here. So first, we have this triangle. and this coordinate over here will, this thing over here will have the coordinates 1 and tangent of theta, just per definition. And within this triangle, we have a circle sector. I can't draw very well, but I hope you get the point. We have a circle sector within it, goes over here. And within this circle sector, we have a triangle. I didn't draw very well, but you can imagine this is a straight line instead. Now, since this is within the unit circle, all of these have a width of 1. So the area of this larger green triangle will have area 1/2 times base times height, 1/2, and its base is just 1 since it's the unit circle, and its height will be tangent of theta, and this will be greater or equal to the area of this smaller circle sector, which will have the area 1/2 times theta, because normally the area of a circle sector is 1/2 times the angle multiplied by the radius square, but again, we're in the unit circle, so the radius is just 1 and 1 squared is 1. And this circle sector must be greater or equal to this smaller blue triangle within it, and the area of a triangle is still 1/2 times base times height. So 1/2, we're still in the unit circle, so the base is 1, and just by definition, its height will be sine of theta. And yeah, I'm assuming that we're always in the first quadrant for these inequalities to hold, so the shapes work out. So we're always somewhere in here. Now we can multiply each of these by 2 over sine of this angle, theta, and we see that tangent of theta over sine is just 1 over cosine, and 1/2 times 2 is just 1. So we have 1 over cosine of theta will be greater or equal to 1/2 theta multiplied by 2 over sine of theta, just be theta divided by sine of theta, which will be greater or equal to 1/2 sine of theta multiplied by 2 over sine of theta is of course just 1. And by the way, for this first inequality, I need the greater or equal to, because when theta is 0, then all of these are 0, so they can be equal to each other. It's not a strict inequality. And now if we take the reciprocal of each of these, that should flip the inequality signs, and we see that cosine of theta, because that's the reciprocal of 1 over cosine of theta, will be less or equal to sine of theta over theta, which will be less or equal to 1. Now, for each of these, let's suppose that the limit of theta is approaching 0. And we have to assume that it's approaching 0 plus, because we already said that we were in the first quadrant. So it's approaching 0 from this direction. So the limit of theta approaching 0 plus of cosine of theta will be less or equal to limit as theta is approaching 0 plus of sine of theta over theta, which will be less or equal to the limit as theta is approaching 0 plus of 1. The limit as theta is approaching 0 plus of cosine of theta, we can just plug in the 0 because cosine of 0 is defined. We have that 1 is less or equal to the limit as theta is approaching 0 plus of sine of theta over theta. And for this thing, 1 doesn't, we just have a number, we just have a 1. It doesn't, the expression doesn't contain any thetas, so we might as well just ignore the limit. But the inequality still holds. This is less or equal to 1. Now, if this limit is greater or equal to 1, but also less or equal to 1, then by the squeeze theorem, this limit itself must be equal to 1. If it's mashed between 1 and 1, then this limit itself must be equal to 1. That's the only thing that makes sense. Now, this isn't exactly what we wanted. We wanted the limit as theta of, we wanted the limit approaching 0, not 0 plus. But what happens when it is approaching 0 minus? Suppose that we have the limit as alpha is approaching 0 of 0 minus of sine of alpha over alpha. This will be equal to the limit as theta is approaching 0 plus of sine of minus theta over minus theta. You see, it's the same thing. If this is approaching 0 minus and this is approaching 0 plus, we can just put a negative sign in front of it, and they are really the same thing. But sine is a symmetrical function, so this is really just equal to the limit of theta approaching 0 plus of negative sine of theta over negative theta. But Since we have a negative both in the numerator and the denominator, they take each other out. So this will be equal to the limit as theta is approaching 0 of sine of theta over theta, or the limit as theta is approaching 0 plus of sine of theta over theta. But we had already established that this was equal to 1 by this thing over here. So really, it doesn't matter from which direction you are approaching 0 from. So therefore, we can conclude that the limit as theta is approaching 0, it doesn't matter if you're approaching it from 0 plus or 0 minus, of sine of theta over theta is equal to 1. So if you just look at this figure, it doesn't matter if it's approaching 0 from this direction or this direction. The limit of an angle approaching 0 of sine of that angle divided by that angle will always be equal to 0 as long as the angle is approaching 0. So we can go back to our what we had written previously and say that this is just equal to 1. And now that we know this, we can move on to proving this limit over here. And I won't draw any weird shapes or anything. I think it's easiest to just approach it purely algebraically. So we have let's say we have the limit of theta is approaching 0 of cosine of theta minus 1 over theta. And now let's multiply both the numerator and the denominator by the conjugate of the numerator, that is cosine of theta plus 1. But this will be equal to the limit as theta is approaching 0. And in the numerator, we just have a difference of 2 squares. We have cosine squared of theta minus 1. And in the denominator, we have theta times cosine of theta plus 1. But we can simplify this a step further by a trigonometric identity. It's the case that sine square of theta plus cosine squared of theta is equal to 1. It's pretty easy to prove if you just think about the unit circle and the Pythagorean theorem. It's just base squared plus height squared plus base squared is equal to the radius squared. which is always 1 in the unit circle. And now we can subtract sine of theta and 1 from both sides, and we find that cosine squared of theta minus 1 is equal to negative sine squared of theta. So if we know this, we can plug back negative sine squared of theta in this numerator. So this is just equal to the limit as theta is approaching 0 of negative sine of theta divide negative sine squared of theta divided by theta times cosine of theta plus 1. And again, I still think it's easiest to split this up into two different limits. This is equal to the limit as theta is approaching 0 of negative sine of theta divided by cosine of theta plus 1 multiplied by the limit as theta is approaching 0 of sine of theta over theta, because yeah, sine of theta multiplied by negative sine of theta is just negative sine of theta squared. And of course we just had a theta times cosine of theta plus 1 in the denominator. For this limit, we're fine with just plugging in a 0 because we don't get, it's not undefined, and we've already established that this thing was equal to 1. So this entire thing is just equal to sine of 0 is 0, cosine of 0 is 1, and 1 is just 1. So this limit is just negative 0 over 2, which is just 0 multiplied by, and as we've already established, this thing is just 1. So this is equal to 0 times 1, which is of course just equal to 0. So now we have established that this limit is equal to 0. So now we can proceed with our proof for the derivative of sine of theta, which will be equal to sine of x times 0 plus cosine of x times 1. And this is, of course, just equal to cosine of x. And we are done. The derivative of sine of x is equal to cosine of x. And the fact that the derivative of sine of x is cosine of x really makes a lot of sense if you just think about it purely graphically. This green graph is sine of x, and the red one is cosine of x. And look at this. When sine of x reaches its steepest slope upwards right here, then cosine of x reaches its maximum when cosine of x is equal to 1. And then, as it continues going upward, but less steeply than before, then cosine of x is still positive, but it takes on smaller values than it did at its maximum. And right here, when the tangent line becomes flat, that happens exactly when cosine of x crosses the x-axis. That is to say, when cosine of x is equal to 0. And then, as the slope becomes negative, cosine of x takes on negative values as the slope continues going downwards. And right here, when sine of x reaches its steepest downward slope, then cosine of x takes on its minimum value of -1. And then as the slope becomes less steep but is still going downwards, cosine of x is still negative but takes on greater values than its minimum. And then when the tangent line of sine of x becomes flat again, then cosine of x crosses the x-axis again. That is to say, cosine of x is equal to 0. And this is exactly the behavior that you'd expect of a derivative. And onto the next function, which was the derivative of arcsine of x. And I think the easiest way to do this is by implicit differentiation again. Uh, I will set y to be, I don't know why I can't draw. Hello? Paint isn't responding. I will set y to be equal to arcsine of x. Let's take sine of both sides. So we'll get sine of, or actually, let me write it further to the right. Sine of y will be equal to, and sine of arcsine of x will just become x again, since they are inverses. And that's just how inverses work. So sine of y will be equal to x. Now let's take the derivative of both sides. On the left-hand side, we've already established that the derivative of sine of x is equal to cosine of x. So the derivative of sine of some function will be equal to cosine of this function multiplied by the derivative of what is inside of derivative of the function of what is inside of this sine. So I'll just write that as dy dx, which is the derivative of arcsine of x, which is really what we're looking for, will be equal to, and on the right hand side, we just have the derivative of x, which is just equal to 1. And we can divide both sides by cosine of y, and we'll see that dy dx is equal to 1 over cosine of y. And now I will use the trigonometric Pythagorean identity again. So if we know that sine square of y plus cosine square of y is equal to 1, then cosine square of y will be equal to 1 minus sine square of y. And if we just want to break out cosine of y, we can see that cosine of y will be equal to either plus minus of, of the square root of 1 minus sine of y squared. Sine, maybe you can't see everything. Let me move it. Yeah. But what is this y? We said that y was arcsine of x. Arcsine of x, it's just an angle. However, this angle, let me draw a unit circle. Arcsine is only defined between pi halves and negative pi halves. So arcsine of x can only partake angles in here. But notice, if we take cosine of any of these angles, it's always positive since it's always on the positive side of the x-axis. So we may just ignore the negative root and just say that cosine of y is equal to the square root of 1 minus sine of y squared. So let's plug that back in. This is equal to 1 over the square root of 1 minus sine of y squared. But what is this y? This y was just arcsine of x, which is what we started with. So we might as well just plug in arcsine of x here. And again, sine and arcsine are inverses. So we just get back our x and take it squared. So this entire thing is just equal to 1 over the square root of 1 minus x squared. And we are done. The derivative of arcsine of x is equal to 1 over the square root of 1 minus x squared. And yeah, that's it. I think I'm done with everything. So, thank you for watching.